Good morning, everyone. Am I audible?
Yes, sir.
Hello? Am I audible? Please say something.
Yes, sir.
Okay. So, I'm sharing my screen. Please let me know if it is visible to everyone. So, is my screen visible to everyone? So, in the last lecture, we discussed geometric application of Hahn-Banach theorem. And what was that? Let me recall it. So, the theorem says that the theorem says that if we have a non-linear space and we have a open ball, say we may have closed ball. So this is convex set. This is a convex set. Okay, a ball is always convex. And if we take any arbitrary point in the boundary of this set x naught, say x naught belongs to boundary of this ball of radius say r, this radius is say r, okay, then there always exists a hyperplane, a supporting hyperplane at x naught. So we always get a hyperplane. This is a hyperplane supported at x naught. This is what we have done last time. So let's move ahead and see another theorem.
सर अगर सेट कॉन्वेक्स ना हो तो फिर क्या होगा?
ओके, से सेट कॉन्वेक्स नहीं है तो क्या होगा? तो ऐसा हाइपरप्लेन एग्जिस्ट करना नहीं कर पाएगा, क्योंकि ऐसा सिस्टम ऐसा कुछ आ जाएगा। मान लो ये आपके पास सेट है, ये कॉन्वेक्स नहीं है, ठीक है। इस पॉइंट के लिए मान लेते हैं, ये वाले पॉइंट के लिए आपके पास ऐसा कोई भी हाइपरप्लेन नहीं होगा जो इसको सपोर्ट करता हुआ, क्योंकि यहाँ पर जो हाइपरप्लेन होगा वो इस फॉर्म का होगा और इसको कट करता हुआ जाएगा। ये देख रहे हैं आप?
यस सर।
इसको कट करता हुआ जाएगा ना?
यस सर।
ओके, सो ऐसा हाइपरप्लेन नहीं मिलेगा, जबकि इस पॉइंट के लिए एक ऐसा सपोर्टिंग हाइपरप्लेन मिल सकता है जो कि ये होगा, ठीक है। कॉन्वेक्स के केस में क्या होगा कि बाउंड्री के हर एक पॉइंट के लिए आपको सपोर्टिंग हाइपरप्लेन, जब नॉन कॉन्वेक्स सेटिंग है तो वहां पर नहीं मिले, ठीक। ओके, सो लेट्स add okay, let's next theorem says that we have a non-linear space over a field K, X non-linear space over a field, and M be a subspace of X. Okay. Now, if you have a point X naught in minus m, so outside m, such that the distance between x naught and m is always positive. And say this distance is d. Suppose d is always positive, then there exists a linear functional, a bounded linear functional g, bounded linear functional on x, such that what happened? So this means it separates. So there exists a bounded linear functional which separates x naught and m. Okay. So this means gx equal to 1. So gx not equal to 1. Gm equal to 0. So what does it mean by Gm equal to 0? This means G of M equal to 0, and this is true for all elements of capital M. And third thing is norm of G equal to 1 by D. Okay. So let's do this. Let's see a proof of this theorem. Proof is very easy. See, it is say let's first draw a rough figure of this. Say we have this is say our M. This is a point x naught. This is point x naught. Okay, and you see the distance is always positive. Distance is always positive. So you know what should be the distance. Distance would be, when we are in R3, the distance would be this length of line segment which makes a right angle with this blue line. Okay, so this is the distance d and it's positive. So what you do, you consider a subspace which is span of M and x naught. Okay, so this means you will get a two. So in this rough sketch, M naught is a two-dimensional space which is spanned by this M and this x naught. Okay, say M is this. So this is nothing but M plus x naught. Okay, you all know this. Now we have D is the distance of x naught and M, and it is always positive. So this shows that x naught does not belong to M. If see, recall this, if dx naught M equal to 0, what does this mean? This means x naught belongs to M bar. Okay. So here this does not, even it does not belong to M bar. Correct? And you have, you know this thing that since M naught is span of M and x naught, each element of x naught, any x in M naught, can be expressed uniquely as a linear combination. Any x in M naught can be expressed uniquely like this: M plus alpha x naught, where M comes from capital M and alpha is any scalar in K. Now we define, so here what is our claim? Our claim is to get a bounded linear functional. So, and we want to use Hahn-Banach theorem, correct? So what we do, we first construct a bounded linear functional on M naught. M naught is a subspace. So what we do, then Hahn-Banach theorem says that if we have a bounded linear functional on N naught, then we can extend that linear functional to whole of X. Okay. So first define a linear function, bounded linear functional from M naught to K. Okay. Consider M given by f of x, but you know x can be written in this form, m plus alpha x naught, and it takes values in K. So see, in this expression you have a scalar value, that is alpha, and this alpha is unique for x. So fx would be alpha, defined like this. So clearly this is f is linear. Clearly f is linear. Okay. Linear on M naught, and say if alpha equal to 0, then x equal to m. Put alpha equal to 0 here, you will get x equal to m. So this means f of m equal to 0. And this is true for all m in m. Not for all m in m. This implies f of capital M is 0. Correct? And if m is 0 and alpha equal to 1, in this expression, in this linear combination, then see what happens. So m equal to 0, alpha equal to 1, x naught. So this is x naught. So when you apply f on x naught, you will get f of x naught equal to 1. So something, so condition, so 1 and 2 is almost done. Okay, so if we can find an extension of this small f to whole of x, then we are almost done, because we have shown that f takes value 1 at x naught and f takes value 0 on whole of m, capital M. Correct? But another thing, whether f is bounded or not, let's see that. Mod of fx equal to mod of alpha. This is true for all alpha in M naught. This is by definition. Okay? So if alpha is non-zero, what happens? Then, okay, then norm x equal to norm m plus alpha x naught. Take alpha common, so you will get mod alpha m by alpha plus x naught. See here. So you know this, minus of norm x is norm x, correct? You all know this. So I'll use this inequality here. So this will be mod alpha norm minus m by alpha minus x naught, correct? So this is mod alpha norm. Now take minus m by alpha minus x naught. So this is an element of capital M. This m by alpha, since m belongs to capital M, and capital M is a linear subspace. So any scalar multiple of small m will again in capital M, because capital M is a linear subspace. So this means this part belongs to capital M. And you know how do you define dx naught M? This is infimum over all m minus x naught, where m belongs to capital M. And since this is positive, this was, you defined this as D, and this was positive, correct? So from here, this is an arbitrary element of capital M, sorry, a particular element of capital M. So this means this D is always less than, this D is always less than minus m by alpha minus x naught. This is by definition, correct? A little digression. So from here, what you get, this is greater than mod alpha D is less than, say less than, it may be equal to, so greater than equal to mod alpha D, and this D is positive, you know, and this is nothing but D mod fx, and this is true for all x in M naught. So one part is done, because what you have proven just now is mod of fx is less than equal to norm x 1 by t. Okay, this is when alpha is non-zero, and when alpha is 0, you know, then x equal to m plus 0 dot x naught, which is equal to m, and you know fx equal to, in this case, is 0. So this means fx is, so this means norm x equal to norm m. It's definitely greater than 0, but this is d into 0, but 0 is f of x, not correct? So when alpha is 0, there is nothing to prove, because mod of fx is less than this. So in either case, so it would be this. So in either case, here when alpha was non-zero, we had this inequality. When alpha equal to 0, we have this. So this means f is bounded. Means f belongs to x dash. Oh, sorry, not x dash, but m not dash. Okay. And norm of f is less than equal to 1 by d. What we wanted to show is this norm equal to 1 by d. So what we have to prove, now we claim that norm of f is also greater than 1 by d. So for this, what we do, we consider a sequence mk inside M, capital M, such that the distance between xk and x naught and mk, which goes to d, because the distance between x naught and capital M is d. So suppose this is the sequence with this condition, with this property, that what we have, then what would be f x naught minus mk? So here, see, for any x which is of, oh, this is of this form. This x naught minus mk is of this form, mk plus 1 dot x naught. So what would be f of x? F of x would be this. This is alpha. This is 1. Correct? Alpha here. Alpha is 1. So this means f x naught minus mk is nothing but 1. Correct?
1 also.
Any doubt?
No, sir.
This 1. So take modulus of this, and this is less than equal to norm f of x minus k. But this goes to d, and d was the infimum. Okay, d was the infimum. Correct? This to edge a goes to infinity. So far, is it okay? Is this okay? So what do you get from here? Get from f less than 1 by d. So this and this, these two will imply that norm f equal to 1 by d. Correct? So far what we have a linear functional on m naught, the subspace of x with this property. F not equal to 1, f capital M equal to 0, and norm f equal to by d. Okay, now use Hahn-Banach theorem from Hahn-Banach. Hahn-Banach theorem for norm displacement. Okay. So far you have seen 3 Hahn-Banach theorem. So first one was it was for linear functional on vector spaces. Okay, extension of linear functional on vector spaces. Second, it was generalized Hahn-Banach theorem when you took a complex vector space. And third one was Hahn-Banach theorem for non-linear spaces. Correct? So norm spaces, so you will get there exists a G from X to G is in fact bounded, and G restricted to M naught equal to F. But you know, G of X naught will be F of X naught, and G of M would be F of M for all M. And you know the values of Fm. Fm equal to 0 and F of X naught equal to 1. Hence proved. Any doubt? If any doubt, please ask. So let's see some application of this theorem that we just proved. let's see some corollaries of this theorem. There are very beautiful corollaries. Okay, so first corollary is, so again we have X a non-linear space over a field and M a subspace of X. Now if X naught belongs to X such that D of X naught comma M is positive. It's the same thing that we took above theorem. Then there exists G dash in there exists G in X dash means there exists a bounded linear functional on X such that number one, G X naught equal to D, second G of M equal to 0, third one is norm of G equal to M, sorry, norm of G equal to 1. See, in the above theorem, what was the conclusion? You got G with this property, G of X naught equal to 1, Gm equal to 0, norm G equal to 1 by D. Okay, so you to make guess from here itself. See, from this theorem, you will get a bounded linear functional with this property. Now you have just do one thing. So whatever bounded linear functional you are getting here, multiply that by D. Okay, so you will get this part. Let's see how. Proof. So since D, which is D X naught M, is positive. Okay, so I think I have made a mistake in notes. Make it X naught in X in the notes. Okay, so I had written X naught in M. This is not correct. Write it X naught in X. If X naught in M, then this dx naught M would be 0, but here it is positive. So please, so I have already, as before I told you that there might be some typos in notes. Please pardon me for that. Okay, and while reading and while writing the notes, please make them correct. Okay, so so from our theorem, there exists an f in X dash such that f of X naught equal to 1, f of M equal to 0, and norm F equal to 1 by D. Now you define a G in X on X to K, define a G such that G of X equal to D dot Fx. Okay, then we are done. How? G of X naught would be D dot F of X naught. F of X naught is 1. 1 is D. Clearly, Gm would be D dot Fm, and you know F capital M is 0, therefore Fm equal to 0, D dot 0 equal to 0. And what is norm G? This is norm D dot F. This is D, B is positive, norm F. But you know here, norm F is 1 by D, D by D equal to 1. Correct? Okay, so another question. So now see a question. There is a question. So we have a non-linear space over a field here I am writing something. M is closed linear space. Okay, closed linear space of X, closed linear subspace of X, and X not in X minus. If D is distance between X and M, then there exists G in X dash such that number first Gx not equal to 1, Gm equal to 0, and third one is norm G equal to 1 by D. It is very easy here. Recall a result from metric space theory. So if you have a closed set, here M is closed, and X not be any point. If if this is 0 for or any set M and any point X naught, if D M X naught equal to 0, then X naught belong to M bar. Correct? So this comes from metric space. Okay. If M is closed and X naught does not belong to M, then Dm x naught is positive. And say if this is D, so in this question, this part M is closed and X naught belong to X minus M gives you that Dm x naught is positive. Correct? So see this corollary. Here you have subspace and the distance is positive. Then G with this property. D x naught in D is positive, then you will get a bounded linear functional with these properties. So since you just write solution, so since M is closed and X naught not belong to M, then P is positive. Therefore, from above theorem, whichever that theorem is, there exists a G in X dash such that G of X naught equal to 1, G of M equal to 0, and G equal to 1 by D. Correct? Okay. Next theorem is also easy. Sorry, next question is also easy. So here, what is the question? Let me write it for you. So X norm linear space, M a closed. So this M is closed. Closed linear subspace of X and X naught not in M. This clearly means dx naught M is positive. Correct? So from above theorem, you may get X naught is G of X naught is 1, and you know this is non-zero. Gm is 0. This is easy. Last question. What does it say? It says X be a norm linear space, X norm linear space, and M subspace of X. Here, this is only a subspace of X, but there is one more property of this. It says M is not dense in X. M is not dense means M bar is not X. M bar is not equal to X. Then there exists a non-zero bounded linear functional such that Gm equal to 0. Okay, let's do this. So you all know, you have seen this before, that if M is a linear subspace, then M bar is also a linear subspace. Then M bar is also a linear subspace. Okay, I'm just telling you the solution because I will be, by that time I would be charging my pencil because the battery is down. So what you do, so please write yourself. I'm only dictating, okay? Down. See here what you have. You have a linear subspace. You know, if M is a linear subspace of a non-linear space, or any okay, M is linear subspace of a non-linear space, then its closure M bar is again a linear subspace. You have seen this. It is given that M is not dense in X. This means M bar is not equal to X. Correct? This means there exists some point X naught in capital X such that X naught does not belong to M bar. It shows that distance between X naught and M bar is positive. Okay? So use last result. Then you will get that there exists a linear functional G on whole of X, a bounded linear functional, such that G X naught equal to 1, G of M equal to 0. That's what we wanted to show, because when G of X naught equal to 1, this means G is non-zero linear functional, and it takes value 0 on each point of M. Correct? Do you see this?
Yes,
हेलो,
आप लिख रहे हैं क्या?
मैं लिख नहीं रहा हूँ क्योंकि मैंने बोला ना, मैं मेरी पेंसिल की बैटरी डाउन है, तो मैं
ओके सर,
चार्ज
ठीक।
करता हूँ।
हाँ सर।
अच्छा, चार्ज हो जाए उसके बाद मैं ये नहीं लिख रहा था, मैं केवल आपको हिंट दे रहा था, आप लोगों ने शायद देख लिया होगा। ओके, सो नेक्स्ट, do you all know what is a separable space? Hello, खुशबू? What is a separable space?
टेबल होता है और
हाँ, बताइए। Anyone? हाँ, what is a separable space? हेलो, किसी को नहीं मालूम? रामजीवन?
यस सर।
सेपरेबल स्पेस क्या होता है? व्हाट इज द सेपरेबल स्पेस?
सेपरेबल किसी स्पेस को कोई कनेक्टेड स्पेस, यूनियन के फॉर्म में नहीं लिख सकते हैं वर्ड।
ऐसा है क्या?
डिसजॉइंट नंबर फर्स्ट, उसके
होना
दो
चाहिए।
डिसजॉइंट सेट होना चाहिए वो।
एक मिनट रामजीवन, क्या आपको ये मालूम, आप शायद किसी दूसरे क्वेश्चन को मिक्स कर रहे हैं? ऐसा नहीं है। आपने ये पहले पढ़ा है सेपरेबल स्पेस?
सर पढ़ा है,
कहाँ पर पढ़ा है?
टोपोलॉजी में।
सर
टोपोलॉजी में, बहुत बढ़िया, टोपोलॉजी में पढ़ा होगा। हाँ, कोई कुछ बोलना लेकिन आप थोड़ा भूल गए उसको।
नहीं,
सर
कोई ऐसा
काउंटेबल
सेट की यूनियन के
हाँ,
फॉर्म में।
नहीं नहीं नहीं, ये किसी ने कुछ काउंटेबल बोला, वो शायद सही जा रहे हैं, बोलने दो।
सर
जिसने काउंटेबल
सबसेट
बोला वो
काउंटेबल होना चाहिए और उसका क्लोजर पूरे आर के इक्वल होना चाहिए।
फिर से बोलो, फिर से बोलो, फिर से बोलिए। आपने एक पर्टिकुलर एग्जांपल दिया ना, ऐसे सभी ऐसे स्पेसेज को सेपरेबल स्पेस कहेंगे जहां पर क्या होना चाहिए?
काउंटेबल हो और डेंस सबसेट।
काउंटेबल क्या होना चाहिए? काउंटेबल क्या होना चाहिए? Okay, if a space has a countable dense subspace, then those spaces are called separable spaces. For example, space of real numbers. तो रियल नंबर के पास एक काउंटेबल डेंस सबस्पेस है. What is that? That is rational numbers. Rational numbers are countable and it is dense in R. Therefore, R is separable space. Correct?
Yes, sir.
So, the definition of separable space is there exists a space X is called separable if there exists a subspace, say M, such that M is countable and M is dense in X, means M bar equal to X. Okay? So, our next theorem is about separable space. Okay, what does it say? It says that if we have a non-linear space and we see its dual space. Okay, if dual space is separable, then the original space is separable. This is our next theorem. So X a non-linear space and X dash dual space of X. Correct? Then if X dash is separable, if X dash is separable, then X is separable. Okay. So here I wrote if X dash is separable, then X is separable. I didn't write X is separable implies X dash is separable. This is only one way implication. Okay. So X dash separable implies X is separable. This way is not true in general. So this is an exercise for you. If there is time, I will tell you an example. If there is no time, then I will skip it. This is an exercise for you then. Okay. So let's see a proof of this result. So this is your exercise. Okay. So let's see a proof. So we are given that X dash is separable and we want to show that X is separable. So what will be proved? What we have to show? Please say, Soumya, please tell us.
Sir, we have
our
to
aim.
show that कि X का कोई भी एक काउंटेबल डेंस सब स्पेस होगा
हाँ, हमें एक सब स्पेस
अगर M मान लेते
एक्स में एक,
हाँ।
हाँ M मान लेते हैं, M एक सब स्पेस ढूंढना है X में जो कि काउंटेबल हो और M बार इक्वल टू X हो,
X
M काउंटेबल, ठीक है, ओके, ये हमारा क्लेम है, बट we know that X dash is separable, so this means X dash के पास पहले से ही एक काउंटेबल सेट है जिसका क्लोजर X dash है, ओके, since X dash is separable, there exists a countable set. You all know elements of X dash are linear bounded linear functionals. वो functions हैं X से field K में, okay. So say this is the set S whose elements are functions from X to K. Belong to X dash, इसको ऐसे भी लिख सकते हैं, here n is any positive. Okay, so we have a countable set inside X dash such that S bar equal to X dash. Okay, this comes from separability of X prime. Now what? Do one thing. So corresponding these fn's, you choose xn's. Okay, so choose xn. So these xn now are inside X. Choose xn such that number one, norm of xn equal to 1, and second thing is fn xn then what you do now, you have a sequence in X. You know sequences are always countable. Is it correct? A sequence is always countable. Hello? Ramya, is it correct?
Yes, sir.
Sequence is always countable because positive integers are countable. Now, consider the closed subspace generated by these sequences. So, consider M, that M is span of all the xn that we just showed, okay, and closure of. So this is clearly M is closed subspace. Okay, if okay, now assume F is, so assume M is not equal to X. And what happened? Then there exists a point not in X minus M. M is closed and X naught is outside M. This means that this distance is always positive. From our theorem, there exists a G in X dash such that G of X naught is non-zero and G of M is 0. Correct? Okay. From here, what you get, from here you get g of xn. Since m is span of these xn's, so xn clearly belong to m. G of xn equal to 0 for all n plus, and from here norm of fn is mod fn x, and you know so this is mod fn xn minus 0. You can write fn xn minus this 0 is g of xn. Okay. So this will be fn minus g of xn. Okay. And use this inequality, norm xn. But you know, norm of xn is 1. So this is nothing but norm. So this is a small calculation, means it's easy to see. From here you will get this fact. Norm g, you may write it like this, norm g minus fn plus fn. So you all know norm of x equal to norm of minus x. You all know this. So this part is g minus fn. Oh, sorry. Fn. This is same as fn minus g plus fn. Okay, use this inequality here. 1 by 2 norm fn is less than equal to norm fn minus g. So it will be okay. It would be 3 fn minus g. Correct. This is for all n in z plus. Okay. Correct. So how? Let's do it again. So this write this correctly. From here, you will get norm of fn is equal to 2 of norm fn minus g, but this is equal to okay. So here I again made a mistake. Please correct that. This is not half. This is
2 times.
this is 2 times fn minus. Okay. And this is true for all n in z plus. But you know, s bar is not equal to x dash because, oh, sorry, s bar equal to x dash because x dash is, so because x is dense. So you have a countable dense subset x dash, so s bar is x dash. So this implies g equal to 0. Why? Do you see why?
क्लोजर में बिलोंग करेगा तो
ओके, ये इसकी मदद से
पर स्क्रीन तो दिख
okay. So this implies g equal to 0, which contradicts our assumption because okay, which contradicts our assumption. Hence m equal to X. So you know M bar, M is closed, implied M bar equal to X. So this means M is dense in X. In fact, M is equal to X. Super. Okay, so this is it for today. So I gave you an exercise. In fact, I have written a solution of that note. Please see it, read it carefully. If there is any typo, correct it yourself. Okay. So while writing, I made some mistakes. Okay, then drop your attendance. We'll meet tomorrow, and then tomorrow we will finish this this unit 2. Tomorrow will be the last day for unit 2, and then we will see Hilbert spaces. Okay, then bye.